Okay, we've hit the last section of Chapter 7, Zeros of Polynomial Functions. We want to be able to, as you can see, use the rational root theorem, which we've been using, and the complex conjugate theorem to find the zeros of polynomial functions. Use the fundamental theorem of algebra to write a polynomial function given sufficient information about zeros. That second one is basically, if they tell us the zeros, we can write the equation. The first one is we have to find what the zeros are and then write the equation from that. So we're going to do both processes, forward and backwards, as they say. And we'll start with the idea of, look at this pattern. 3x squared plus 10x minus 8 equals 0. Regular trinomial, second degree equation. It factors quite nicely into the quantity 3x minus 2 and x plus 4. You can use your trinomial factoring skills to do that. From there, we find the zeros. 3x minus 2 turns into a 0 of 2/3, and the x plus 4 quantity turns into a 0 of -4. Now, what I want you to look at, there's a pattern here. And if you don't see it, we need to identify it. Notice that the numerators, 2 and -4, are factors of that constant term, which was 8. So the numerators came from this constant term. Also notice that the denominators, the 3 and the 1, were factors of that leading coefficient of 3. So the denominators came from the 3's factors. So that's really important. And that happens every single time on a trinomial when you're finding the zeros. The numerators come from the constant, last term, like people like to say, and the denominators come from the first term. So you're going to see that pattern used in what we call the rational root theorem. Let p be the polynomial function with the integer coefficients. So we've got whole numbers in standard form, and if p divided by q is a root of the polynomial only if it comes out to 0, which is what we've been saying. We can't have any remainders, but we've said p is a factor of the constant term, which some of you would like to say is your last term, where q is a factor of the leading coefficient, and most people would like to call that the first term. So when we say p divided by q, some people like to think of it as last over first. This theorem can be used to identify possible roots of a polynomial equation. Now remember, just last week, early in the chapter, we couldn't always factor everything. We were trying to find roots. So now we have synthetic division, long division, and for some people that's a tedious process. Is there something else we can use? So here today is another possibility, but you have to be able to find the possible roots before you can find the actual roots. So let's go there on an actual problem. So to find all rational roots of, here's our polynomial, 8x squared plus 10x squared minus 11x plus 2 equals 0. I think I said 8x squared and it's 8x cubed. So it says first list the possibilities. So you got to be thinking that p over q combination. And so the p is really our last term factors, and the q is really our first term's factors, so 8. And so now I'm going to list those factors, and then we'll list all the possibilities out there. So the factors of 2, 1 and 2, the factors of 8, 1, 2, 4, and 8. So now if we listed all the possibilities, and yes, I'm going to have plus and minus on all these, we could do 1 over 1, plus and minus 1 over 2, plus and minus 1 over 4, plus and minus 1 over 8, and then go the last route, and that would be plus and minus 2 over 1, plus and minus 2 over 2, plus and minus 2 over 4, and plus and minus 2 over 8. Now looking at those and trying to write our final after we eliminate any repetitive ones, That means we'd have a plus and minus 1. We'd have plus and minus 1/2, plus and minus a quarter, plus and minus 1/8, plus and minus 2. Then 2 over 2 is the same as 1, 2/4 is the same as 1/2, and 2/8 is the same as 1/4. So we're going to cross all those out as already have. So really what it boiled down to, we have 10 possibilities of roots. Now, with 10, that's a lot of them to check. You'd have to put them in there, do your substitution. So I like to say, let's get a visual. Let's get a peek, a chance of picking some good choices instead of having to do all 10. So next step is we need to check our graph. So I have one for you. You can graph it on your graphing calculator, but I believe here is the 8x cubed plus 10x squared minus 11x plus 2's graph. You can see we have 2 turning points. It's one of those S graphs, and the key features in it currently are we're looking at possible zeros. So right now you have to be focused in here and here. And we're counted by 1s, but actually no, they're counting by 2s. But let me move this up and let's zoom out a little and see if we can get a little better view of this graph. So here we go in, see if it'll adjust for us. Here we go. Now my green dots are going to be off, so let me erase those. So now actually we can even see a little better situation, and let me erase those because now they're in the wrong spot. So it's looking a little better. Right now, with a zoomed in look, we can see that we have probably that -2 is going to be a really good choice. And then over here we have 2 things happening, but we can't tell what size those numbers are. So we got 2 positive values here that we'll have to get some other way more accurately. But let's use this peek or cheat, I like to call it, using a calculator. We got a really good idea that it's -2. So let's go back. And now, knowing when we check the graph that it appears that -2 is a good choice, we should now be able to do synthetic division on our polynomial with our value of -2. So that's what we're headed towards now. And so we will put our coefficients in, 8, 10, -11, and 2, because everything was in descending order. And now we'll start the synthetic division process. So bring down that first number, 8, start your multiplication. -2 times 8 is 16. Add these 2 numbers together. Oops, sorry, that's a -16. Make sure you don't make that mistake because we will have an error. Now, 10 plus -16 is -6. -2 times -6 is 12. Add those together, we get a 1. -2 times 1 is -2. Add these together, we get a 0. So we know we have a remainder of 0, which means we have a 8x squared minus 6x plus 1 as a trinomial, and that leaves us the x minus 2 as a factor. Now, in seeing that, the question is, can we factor further to try to find the other ones? We know we've got the x minus 2 taken care of, but this is a trinomial, so we could try our choices. Now, we know we have a 1 and a 1 in the end slot, because those are the only factors. And then more than likely, you're going to use the 4 and the 2 from the factors of 8. Because they're closer together, they give us more possibilities, and it looks like that one's going to do it. Insides would give us 2x, outsides would give us 4x if we make them both negative. Bring our factor back out front. And so from here, all we need to do is find the zeros from each of these, and we can get an x value of 2, an x value of 1/4, and an x value of 1/2. So that would take care of those 2 points that we saw, and we found a very accurate graph. So let's go back to that graph. We now have the -2, the 1/4, and the 1/2 taken care of from our graph, and we are good to go. Let's just double check to make sure we got what they got, and we have the same solutions. Okay, so process again will be similar on this next one. We have a q of x quadratic. This time we're looking at it, again, it's descending order. We don't know the possibilities until we do p over q. So let's look at our values this time. P over q. P, the last term, is a 12. The first term is a 1. That makes it a little better, but listing the factors of p, we get 1, 2, 3, 4, 6, and 12. Listing the factors of q, we have that 1. So really now all we need is the last terms over the first term. So plus and minus all of these. 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, and 12 over 1. And again, yes, all of them are plus or minus. So this time, we have the same total we had last time. Oh no, we have one more. We have 6 times 2, 12 possibilities. So again, the next step would be go to the graph. Go ahead and check your graph. So we will check our graph, and you can see right now, again, without zooming it looks like we have 3 possibilities. We have one here, looks like at a +2. We have one between -1 and -2, and we have one between -4 and -5. So that it looks like we have 3 of them total, but it looks like the 2 is probably the good cheat or peak, it looks like, from our table. So knowing that, let's go back to our problem. And so if 2 is a possibility, a +2, we want to set up, again, synthetic division with our 2. And if we do that, whole coefficients, 1, 4, -6, -12. Bring down the 1 and get started multiplying. 1 times 2 is 2. 4 and 2 is 6. 2 times 6 is 12. -6 and 12 is 6. 2 times 6 is 12. -12 and 12 is 0. So we get a remainder of 0, which is what we're looking for. So we have a factor of x minus 2. We have x squared plus 6x plus 6. And again, real quickly with your factoring skills, you could try to break this up into x and x, but what multiplies to give me 6, 1 and 6, 2 and 3, definitely don't add to give me 6. So we're going to have to go to our quadratic formula in this case. So we would have x equals the opposite of b, plus or minus the square root of b squared, minus 4 times a times c, all over 2 times a. So let's clean this up a little. We can see underneath the radical, 4 times 1 times 6 is 24. 36 subtract 24 would give us a 12. So -6 plus or minus the square root of 12 all over 2. Start looking at that and break that 12 down. We know it's not a perfect square. So think of that 12 as 4 times 3, but that would mean 2 root 3. So if we lose the 12, square root of 12, and replace it with a 2 root 3, you should see that they all can be reduced by that factor of 2. So I believe we're going to end up with a -3 plus or minus the square root of 3. So not a real nice number, but we could go to our calculator and find out what that is approximately. And we said we had some approximates on our graph. So all we need now are what are our zeros, and we already had the 2 as one of them, and now if we add these two values, these are the exact values. Let's check and see. There we go. We got our 2, and then we have the two values right here from our radical look. Okay, nice. So don't think factoring is going to always do it, because it won't. And now we're going to throw one other piece in. What if, because you know this happens, in a quadratic equation, if we get, or a quadratic formula, if we get an imaginary number or a negative number underneath the square root, we could end up with a complex root. So watch and see what this says. If p is your polynomial function, again with whole number coefficients, and a plus bi is a root, so when you do the quadratic formula you end up with a complex number, then we're going to tell you that a minus bi, its conjugate, is also a root. So do not forget that this a minus bi was called its conjugate. So again, if I had the number 3 plus 4i as one of my roots, then I immediately know that I also should have 3 minus 4i. All right, using that, let's go to an example that might show those. Negative 4x cubed plus 2x squared minus x plus 3. Again, same look. Possibilities. We have a few more. We got p and q this time. If we say the p-values are the the p-value is the last term is the 3, the q-value is the negative 4. The p factors are 1 and 3, the q factors are 1, 2, and 4. So we should have 1 over 1, 1 over 2, 1 over 4, 3 over 1, 3 over 2, and 3 over 4. And yes, of course, plus and minus on all of them. So do we have any repeats? It really doesn't look like it. So 1, 1/2, 1/4, 3, 3/2, and 3/4. So again, we have 12 possibilities. So as we say, let's go ahead and look at our graph. Okay, in looking at our graph this time, we see one of our S-shaped curves, but we're only seeing one place, and it looks like it is at 1. So with our quick peek, we're only getting 1, 0. Okay, well that's sort of odd because our equation's so big. So we'll take that one peek, go back, and it looks like it's a positive 1. So we're going to do our synthetic with a positive 1. Here's negative 4, 2, negative 1, and 3. Move the first number down, start your multiplication. 1 times negative 4 is negative 4. Add them together, it's a negative 2. 1 times negative 2 is negative 2. Add them together is a negative 3. 1 times negative 3 is negative 3. Add them together, 0. So we get no solution, no remainder, which is good, sorry. And we have a quadratic that's negative 4x squared minus 2x minus 3. I would probably factor out that negative right away and try to do some factoring with it factored out. We know we could start with a 4 and a 1. We only have the choice of 3 and 1 at the other end. We got to get a 2. We're a little too far apart. So if we use the 2 and the 2 and the 3 and the 1, again, we're still too far apart. So I think we're going quadratic again on this one. So let's try that. Here's our formula. We're going to put the x's or the negatives in. Opposite of b, that would be 2 plus or minus the square root of b squared would be 4 minus 4 times a, which is negative 4, times c, which is negative 3. Scrunch there, sorry. All over 2a, which is negative 8. Simplify me. Do the math. 4 times 4 is 16, times 3 is 48. 4, take away 48, leaves with us a negative 44. Start thinking about that negative 44 because it definitely can be broken down. What are you going to think of it as? Well, hopefully 4 and 11. So if we think of it as 4 and 11, we're going to cross that out and replace it with 2 root 11, 2I root 11. I'm going to write it on the, because it would have been 4, because negative in there. So if we can reduce all of that now by a factor of 2, I think we're going to have x equals 1 plus or minus I root 11 all over negative 4. Looks pretty good. Two solutions along with the one from before. Let's check and see if that's what they have. There they are. We can see we have our 1 right there. We have our 1/4 I root 11 and our negative 1/4 minus I root 11. So we're good. All right, last but not least, let's go backwards. What if they provide us with information for the zeros, and then it's our job to find some equations? So in this case, you're thinking the zeros of a 5th degree polynomial. So you know you have x to the 5th in it somewhere. It's a function called q. It has a 0 of a negative 5 with a multiplicity of 3. Multiplicity of 3 means it occurs 3 times. And we have the imaginary 3 plus I, or complex number. So then we should know from that complex conjugate rule that we also have 3 minus I as a root. And then one of our zeros, q sub 0, will calculate out to equal 2500 in our equation. So we have a couple things to do here. We want to write it in factored form and standard form. Now obviously if we get it to factored form, all we have to do is our algebra multiplication to get it to standard form. So let's check it. Right now, with the information we have a q of x equation. So let's write down what we know. We know q of x is equal to, we have a 5, included, we have a negative 5 as a 0, and it's to the multiplicity of 3. So I know I have 3 of those, and if negative 5 is a 0, that means my factor has to be x plus 5. So I have 3 of those. I'm just going to write it out once. And so also our conjugate, so I know I have an x minus 3 plus I. And we also said that means we know we have its conjugate. So x minus, the conjugate is 3 minus I. So with that, we now have our equation. With one exception, you have to remember that all of these polynomials can graph and get stretched vertically and stuff. So we don't know what value would do that. So we're going to leave up front that a factor that could represent a stretch. It could be a 1 and just leave it as is, but might be a 2, a 5, you know, all options are on the table. So with this, we should now have to do some multiplication to start simplifying, because we want to factor this. We want to get the imaginary numbers out of it. And we'll come back. So I think we can leave this first part, the a, x plus 5, quantity cubed alone. And we can come back and we can talk about multiplying this, which we should be able to use FOIL. They look like two binomials. So here we go. First times first, x squared. Outsides would be plus a negative x. And we could say, let's go ahead and actually multiply it all. So that would be, if you don't want to, that might be too much. So x times the 3 minus I. And then we have another term inside, so plus negative x times 3 plus I. And then last times last would be a positive. Ooh, we can do this. First times first, 9 outsides. Insides cancel, last times last, plus negative I squared. And a negative I squared, we should know, would be a 1. And so it looks like we're going to have a 10 sitting on the end there. All right, let's clean this up a little more. X squared plus negative 3x plus positive xi plus negative 3x plus negative xi plus that 10. All right, let's find some like terms here to clean it up even further. I've got a negative 3x and a negative 3x, a positive xi and a negative xi. We're pretty clean right there. X squared plus negative 6x plus 10. We still have our factor out front of x plus 5, that quantity cubed because of the multiplicity. All right, keeping in mind where we're headed. We could at this point find out if we have an a value other than 1 by taking q of 0 is 2500. So we know if we put a 0 in for x, this answer comes out to be 2500. So I'm going to put 2500 here, and I'm going to put a 0 in for all my x's and see what happens. That would be 0 plus 5 is 5 cubed. And here 0 plus 10 is all we have left, so 10. And 5 cubed is 125, so I think we're looking at a 1250a. And the 2500, that would divide out, and we would be looking at a equals 2. So we could now write our factored form equation in the form of 2 times the quantity x plus 5 to the multiplicity of 3, and then times x squared minus 6x plus 10. That would be our factored form equation, and if we go back up, leave that right there, and try to show, voila, we have the same equation. Now, to go standard, all you need to go standard is to multiply that out. And that's the part you can do. Remember, you can't do any more on these than one at a time. So just multiply it out, that standard form equation, and just give you a heads up so you can check your work should be 2x to the 5th plus 18x to the 4th minus 10x to the 3rd minus 350x squared plus 2500. So again, once you multiply out the factored form completely, carefully, you would get the standard form equation. All right, that's a little practice problems, but bring to class any questions you have, and we should be good to go for some practice on these.